To understand complex numbers, you really need a background in our number system. If we look at the history of numbers, there was a time when all people needed numbers for was counting how many goats they had or how many sheep they had, and all they needed was numbers like 1, 2, 3, 4, 5, 6, and so on. Now, looking back at that today, we use a name for those sorts of numbers. We call them counting or natural numbers. So in this diagram, we're going to use a circle to represent the set of natural numbers. And I put a few representative things inside of the circle. At some point in time, someone decided that they needed a number to represent how many goats they had if they did not own goats. And so the idea of the number 0 came about. If we take all of the counting numbers and incorporate the 0 in with them, we have a set of numbers that we refer to by the name whole numbers. Notice in our diagram, if we take the set of natural numbers, if we take all of those and include the number 0, then we get the set of whole numbers. But then what if we were measuring something on a scale that started at 0, and for some reason we needed to measure things below the 0 mark on the scale? Well, that's where we developed the idea of negative numbers. And so if we take all of the whole numbers and incorporate the negative of those, we get a group of numbers that we now refer to by the name integers. And here's the diagram for that. All the whole numbers are included within the integers. And then the idea came about that we needed to be able to count how much we had if we had portions of whole things. And so the idea of fractions came into play. A fraction is called a rational number, and it's always an integer divided by an integer where the bottom integer is not 0. Here's the diagram for that. All of the integers are within the set of rational numbers. And there have been some things throughout the history of numbers that have not seemed to fit in any of the categories. Here's one of the best examples. For centuries, it's been known that the ratio of the circumference of a circle to the diameter of a circle is a constant number. For quite some time, that was believed to have been 22/7. And in modern times, we know that that is not exactly what it is. It actually comes out to be a number that we call pi, which is about 3.14, but which is a non-ending, non-repeating decimal. That is not a rational number. Here's another one. If you take a square that's 1 unit on each side, the measurement of the diagonal is approximately some decimal value, but it is exactly what we call the square root of 2. There is no exact decimal value for the square root of 2, like there is something like the square root of 4. And there's others that we won't describe at this moment, but the decimal approximations are not exactly what they are. These are referred to by the name irrational, a word that means not rational. Now in our diagram, the irrational numbers are completely separate from the rational numbers. if we combine all of the rational numbers and irrational numbers together into one group, we can give them the name real numbers. And so that's what real numbers are referring to. And of course, there are things that do not fit into that category. For example, the square root of negative 4. It is not a 2 because 2 times 2 is positive 4. And it is not a negative 2 because negative 2 times negative 2 is also a positive 4. So there's no number that multiplies by itself to give a negative 4. We call this a non-real number. I'm just making a play on words here. That is not the actual name. However, we can take any negative number and write it as the product of the positive number and the square root of negative 1. The square root of negative 1 is given a special name. We use a lowercase letter I for that. And so we have these sorts of numbers, which are actually called imaginary numbers, hence the use of the letter I. The usage of the word imaginary has caused some comical type situations. However, you need to remember that the name simply implies a certain kind of number. It is not, as the cartoons seem to indicate, someone's imagination. Here's how it fits with the numbers that we talked about earlier. The imaginary numbers are completely separate from the real numbers, a completely different group. If we combine those two groups together, the real and the imaginary, we get a grouping of numbers that we call the complex numbers. We usually abbreviate complex numbers with an A plus BI. We call the A the real part and the BI the imaginary part. Here are some representative examples of complex numbers. And we want to see how to add, subtract, multiply, and divide complex numbers. I will do all of these by hand, and then I will show you how to use your calculators. So to do the addition of these two complex numbers, we can simply use the laws of algebra and treat the I as a variable by removing the parentheses, which we can do since there's nothing on the front of the first parentheses, and there's a plus in between the parentheses. We can combine the 2 and the 4 together, and the 3i and the minus I together, and there's our answer in complex number format. To subtract these, remember that in algebra, when you have a minus sign on the front of parentheses, you have to distribute the minus sign throughout the parentheses. So we're having to distribute the minus sign, negative 4 and positive I, which simplifies to negative 2 plus 4i. Just like with x's, to multiply these two expressions, these two complex numbers, we just use the FOIL method for the multiplication of two binomials. 2 times 4 is 8. 2 times negative I is negative 2i. 3i times 4 is 12i. And 3i times negative I is negative 3i squared. Now the I squared is quite the issue, but we can combine the negative 2i and the 12i together, And then recognize that the I squared is the same thing as -1. So if we replace the I squared with -1, we can then combine the 8 and the 3 together. If you're going to do division by hand, you need to remember the special trick for doing this. The special trick is to multiply both top and bottom by an expression that looks just like this, but with the opposite sign in the middle. You have to use that, of course, on the top and on the bottom. So multiplying these together on the top using the FOIL method, we get this. Now on the bottom, using the FOIL method, we have 16 plus 4i minus 4i, so the 4i's will disappear, minus I squared. And like we did before, the 16 minus I squared, we can replace the I squared with -1. And then simplify. We typically would write this with the 5 over the 17 and the 14i over the 17. To use our TI calculator for complex number operations, we need to first set the mode to complex mode. If we push the mode key, you notice on the line that starts with the word real, next to it there's a plus bi. If we go down and over to the a plus bi and press enter, now our calculator is in complex mode. We can now do complex number operations. So if I do a square root of -4, my calculator knows that that's 2i. We can enter this complex operation into our calculator just as we see it written. We'll use the parentheses 2 plus 3i. Now the I is up above the decimal key, and we have to push the second key and the decimal to get the complex I. So there's 2 plus 3i plus 4 minus I on our calculator. We can enter this on our calculator as we see it on the screen. Here's 2 plus 3i minus 4 minus I. Similarly, multiplication is very straightforward on the calculator. Here's 2 plus 3i, and then right next to that, in parentheses, we'll put 4 minus I. And you could also use the times key in between those, but you still have to have parentheses on each one of them. Some TI-84 calculators have problems if you try using the fraction template with complex numbers. So the safe thing to do is to enter your complex operations with parentheses and the divide key. Here's 2 plus 3i in parentheses, that's what's on top of the fraction, and then the divide, and then parentheses on the 4 minus I. If you type it like this, I think it'll work every time. Then you can use the math number 1 to transform it back into fractions.